I'll just off the phone. Today today our class is largely to be dedicated on large span shell structures. But before we get into shells, in continuation to where we stopped last time at looking at the theory and some fine examples of tensile and cable state structures. Thankfully, both of us were able to stumble upon a large number of so to say uh, diagrams, tensile and cable state diagrams that we thought we could share with you all today, um, as any kind of awareness or exposure brought about by way of structure should help you. So we've been in a position to compile that. So we'll divide today's class into two parts. We'll run through those. There are not many. There are around um, 13, 12, 13 odd slides of something that we have already seen last time as tensile as well as cable state, largely cable state. I'm sure there'll be an eye opener because we are not going to show you the conventional tensile that is there and certain concepts that are associated. There's a very nice compilation called Structural Systems by Enrich Engel, and we were able to stumble upon them over the week. And so myself and Vikram have decided that we should present those to you first before we get into the other half of the class. That is a lecture on on large span shell construction. Yeah, and and uh, and the and the takeaway of shell construction by way of its both form as well as its conservation on material. Yeah, either of them. So before we get into that, let me just start sharing. Vikram, can I request you to please take the attendance for the day? Yeah, till then I'll.
Jimmy, I have shared the other first and second submission already.
Thanks. Attendance for today. I don't see the download. I don't see the. Yeah, I don't see the download.
I have taken.
Yeah, can you see the Vikram? Can you see the slide?
Yeah. Yes.
I'll go ahead. Yeah.
Yeah.
Yeah. So we'll uh, we'll categorically go through. We'll categorically go through some of the systems that last time he is already introduced, but we need to understand that form making is everything in some sense. Uh, Form making and its support system is everything that goes into the making of the shell construction. Uh, Soap bubble models, yeah, by conceiving the model, by conceiving the form, yeah, with its support system, the tensile strings in place, yeah, very easily one is able to get to visualize in completion a soap bubble model by the experiment, which is very well known, very easy. Most of our final year students, when they have attempted tensile construction, have attempted very successfully, yeah, very successfully soap bubble models, and they have been a big eye opener. They've also brought down the nitty-gritties by way of curvature, by way of support systems. And so here in this diagram, you are in a position to see um, pull down, yeah, pull down anticlastic formed pull down support system whereby you have 4 supports, 6 supports, yeah, and 8 supports and more than 8 supports. And as you see, as the supports increase, yeah, as the supports increase, and you can see here that thankfully, though the spans increase, so but naturally it is understood that as the supports increase to certain extent, the idea that the span can afford to increase to a certain extent, not entirely, because if you span a little too much, perhaps there'll be sagging from the middle, and that's not going to help. That's not going to help in this particular model where you are not pivoting, where you're not pivoting any part of the center. Yeah. So we thought that these diagrams, with the kind of clarity that is there, both in its drawing as in both in its drawing. Yeah. Enrich Angel takes a lot of effort in drawing out uh, both the plan section, yeah, as well as three-dimensional manifestation of the uh, yeah. So he takes the opportunity in drawing these out in thorough detail, thereby helping us visualize. Yeah. So if you look at the support systems, the alternate support system is pinned up. I think Vikram spoke about this in detail last time about how you are in a position to get this saddle-like form by way of pivoting two ends up and pinning down two ends, thereby getting the anticlastic saddle-like structure. The beauty is that spans can increase circumferences. So if you look between 2 and 12, 2 support to 12 support, you can clearly see that you can clearly see the amount of area coverage can increase drastically. Yeah, I'll go ahead. Wait, this does not go ahead. Yeah, that's the other format. That's the other format of the where you have I've arranged it in a manner whereby now you can categorically look at the kind of form making that you'd like to opt for. So here very clearly you are seeing the tent like central pivoted model or typology, you could say. Yeah, whereby you see that, and here it's not the supports, here it's largely to do with the pivots. Yeah, the central pivots, and the central pivots, as we know, is a ring usually from the ring from which the tensile fabric is adhered to and slopes down, and all the ridges, valleys, and the welding of the joints take place. So here are the topmost diagram talks about the various kinds of ties that go about making the pivot. But here we are seeing uh, as good as from one pivot to eight pivot kind of structure. Yeah, along with the idea of along with on to your right, where you see three pivots that can allow for a central well for draining out of the rainwaters or getting in light or whatever that is there. If you look at how well he's detailed out the central opening or kind of an oculus, yeah, it clearly indicates that that's meant for the rainwater to get off without without affecting the because you see that all of that, it turns out when you have three pivots, yeah, when you have three pivots on the on the ends, you but naturally are bound to land up with a valley, yeah, or with a bowl in the center, and that would not serve the purpose. And in such a case, you'd want to puncture it in order to be able to. So if you look at even number, if you look at even number pivots, if the pivots are even numbers like the one above to your right, the diagram to your right above, you will see that pivots are lined up. Yeah. So this also gives a clear indicator that tensile help in being modular and repetitive, thereby giving me linear structures. So here it's very well known that single module repetition is very easy in working with such tensile structures. But if you are able to pair the pivots, yeah, if you are able to pair the pivots and alternate, if you look at how the altering of the, if you look at how the altering of the, so to say, I just go there. If you look at how the altering of the smaller peak takes place as compared to the altering of the larger peak takes place, thereby helping of draining of water on either ends and giving you a symmetrical form. We'll I thought I'll show this diagram since we are talking about pivoted tensiles to clearly indicate that pole centrally pole pivoted, or yeah, or pivots from inside vis-a-vis keeping the interiors support free. So the idea of having the disc, or the idea of pivoting the disc, yeah, from which the seamless material, or the material seamlessly comes down, as you can clearly see. You can see the finish and the seamlessness in which the welding of the fabric has taken place. If you look here from the lower photograph clearly shows that the pivot is suspended, yeah, and the suspending of the pivot here is through a as good as like a triangulated structure from the outside from which the ring can be suspended. The ring can also be suspended by a network of cables. So I could have a network of cables tied at a very high level from which the from which perhaps the from which perhaps the discs or the rings can be suspended, from which perhaps the fabric can come in, thereby making the entire lower floor um, thereby making the entire floor support free. Yeah. So I thought this was important to show you that the pivoting of the ring could either take place from a pole from inside, which is a very normal and standard practice. On the other hand, the ring could be pivoted above by suspending it, yeah, by either suspending it through cables or through triangulated structures from the outside. I thought that was important. Yeah. The next typology, other than being saddle backed and pivoted, is by way of introducing the arch. Yeah. So I'm in a position to create a ridge. The entire exercise is about creating a high point and low point. Yeah, as we've now by now have understood. So you are in a position to create a high point now by not creating a pivot, but by creating an arched ridge. Yeah. So an arched ridge with uh, thankfully you can see very nicely is drawn out along the top arched ridge with 4 supports, with 6 supports, with 8 supports, two arched ribs, two arch ribs with a converging point, two arch ribs with distances between the arches, and two arch ribs with wide apart center, and yet all of them work perfectly well by way of a structure in itself, disposal of rainwater, spanning, etc. And you can see clearly how the footprint, yeah, how the footprint just by the use of two arches or the number of or the spacing of the supports, you can clearly see how the footprint of the enclosure has been worked with and has been enlarged. Yeah. So the arch works in compression. Yeah, the arch works in this. It's a fine system of compression and tension. Yeah, the arch supports. Thankfully, unlike the saddle back, all of these supports are going downwards. Unlike in the saddle back, opposite ones are in the upper direction. That means pivoted. while the uh, other sides are going downwards. Yeah. Similarly, in the pivoted type, you had a very specific idea of the pivot, and you had specific pull down supports. Here, if you look at it, all the supports go downwards, thereby giving you forms very great clarity in form. Yeah. I'm not able to go ahead. Yeah. So here is a, yeah, to your left is to your left is very systematically put across the typologies that we have spoken about. Yeah. Um, and to your top left, yeah, to your top left, are we talk is about talking about giving pivots. How do you provide pivots? Now this is very important. I think this diagram to the left is perhaps the most important diagram to decide on form making by way of either suspended cabled pivots or um, pivots in compression. Yeah. So you are the diagram to the left, the topmost diagrams are showing pivots in compression, vis-a-vis the diagram to the left bottom are showing all pivots created through tension, yeah, suspension, all kinds of. So I think this diagram is I think this diagram is very important to understand how I'm in a position to create peaks in a tensile structure by way of creating pivots, yeah, pivoted points or high points. If you look at the above, we've discussed the saddleback form, the arched form, the pivoted pole from inside, and the pivoted pole in triangulation. Yeah, we've looked at all of them by way of examples. Yeah, pivoted pole in triangulation we just saw by way of the suspended ring. Yeah, the suspended pivot top. I'm pretty intrigued by the lower ones, though I'm sure none of them would be easy to construct, but the lower ones talk about creating multi-pivoted, yeah, modular multi-pivoted, so to say, tops by suspending from a line of cables. I just spoke to you about, I had spoken to you about creating a network of cables along the top, from which perhaps the peaks could be suspended. Yeah. So you'd see them suspending from by way of three peaks, and fine if you just go about analyzing these diagrams, you'd gather that you'd understand best whether your understanding on compression and tension members works well or not. Here are again linear models to the right are both linear as well as yeah. So the topmost is using the linear understanding of creating similarly pivoted linear types. Yeah, very clearly using the end pivots at the ends, or yeah, from which yeah, thereby giving you alternating valleys and gutters. Yeah, very similar to the folded plate that we've seen. Um, as you go ahead, you see form making, yeah, with radially with the idea of the radial rings, yeah, and don't forget that again here alternating. If you look at the section, if you look at the section of the diagram to the right, lower right, you will clearly find that there are alternating members that are high and low. Yeah, alternating members that are high and low, and thereby giving you forms that work well in by way of. Now we come to another segment where you'd not depend on so to say tensile fabric, but cables, cables, and you'd use again the you'd use the arched frame. You'd use the arched frame to be in a position to uh, work with the tension of the cables. Yeah. So arched. So here you do not only see the arched ring used as a pivot, but you also see the arched ring or the arched frame as an edge member. Yeah, that's very important, and that is leading to the forms that we are seeing. Very strong and very uh, and form and time tested forms that have worked well and have been executed. Yeah. So so again saddle. So one at the top is the saddleback roof that is there. The beauty here is that the arched ring is not used. The arched frame is used along the edges, vis-a-vis the arched in the center and the arches in the, yeah, and yeah. So all, I think they speak for themselves, and these have been these have been tried and tested models. Yeah, of, you can look at how the arch rings, yeah, how the arch rings have been how the arch rings have uh, in some sense been reinforced. The arch rings here are in concrete. They could be in steel, they could be in concrete. Arch rings or the arch frames along the outside, and you can look at the tension cable that is there, and translucent roofing system that sits in between. Yeah, all of these. Yeah, here you're seeing the arched ed arch edges spaced apart. Yeah, clearly spaced apart, and thereby getting yeah, indoor qualities. These are well known for indoor stadiums. Yeah, lightweight roofing systems. Yeah, I think it's important to understand them as part of um, the idea is that you're looking at the roofing system now, not depending on tensile fabric in this set of the typology. In this set of the typology, you are looking at creating a mesh, a network or a mesh of cables, which can be perhaps taken care with other material other than tensile fabric. Yeah, I think that typology. This is cable stayed in so we've always heard of cable stayed used only for, we've always looked at cable stayed bridges. Here you have cable stayed in form making, where you have the edge rings, yeah, helping you in form making in some sense. Yeah, and look at them. Thankfully, thankfully he draws out the plans and the sections, thereby helping us understand of what kind of enclosures these kind of forms can help us work with. Yeah, so um, yeah, so point where which are how you'd how he also gives the options of strengthening the arched or the edge frames. How do you, could you, so they could be of solid frames, they could be open webbed, solid webbed. Yeah, the lower one to the left, the lower one to the left is on similar ideas to we've seen earlier. and to the right are more complex forms comprising of repetitive modules that are happening, yeah, be it 3 module, 4 module, yeah, and what I'd urge you to see are the sections that he's drawn. The sections are the sections are where the details lie and how he visualizes them in form making. Yeah, uh, very practical by way of how the roofs would drain off and form making and in form making. Yeah, the to the right lower right is particularly uh, asymmetrical form making. Yeah, that you can clearly see both in its 3D as well as in its section. Yeah. This particular slide clearly shows the process in which the cable stayed is spanned. Yeah, how the members uh, are are looked at and how they are spanned across, because you have to understand that the idea of the tensile comes with the slenderness of the cables and the kind of tension it can take, both in its when it is the kind of tension it can take and create when it is installed or executed. Yeah, only when you have cables that are only when you have cables that are slender can you work with them. Yeah, and so both these diagrams here clearly show. Yeah, both these diagrams here clearly show the kind of tensile supports. Yeah, both tensile supports as well as tensile cables of how they can be used in order to create form making. To the right is more of just assembling the cables, but to the left is again a set of linear typologies that clearly now allow you to use the cable with strutting in between. Yeah. So if you look at all the 3 sections to the left, if you look at all the 3 sections to the left, you will see that now you have double cables. Yeah, you have cables both in the valley, both along the ridges, and you could use vertical struts, yeah, to both hold them in place as well as help in form making. Yeah. So if you look at the diagram, if you look at the diagram to the right, yeah, if you look at the diagram to the right is the idea of how cable stayed. Yeah, how cable stayed can actually help you in some sense. I'll shift this up ahead. Yeah, but cable states can actually help you. Uh, uh, Yeah, by way of edge conditions. I think the edge conditions here, especially in the last 3 diagrams here, is important. Yeah, the 3 diagrams here clearly talk about the varied edge conditions that are there in order to anchor the cables. Here, the cables go beyond the structure to anchor themselves. The second last diagram to the right, whereas here you'd see how the anchoring of the cable takes place with the help of some kind of a diaphragm beam there. Yeah, very similarly seen in the Dulles airport, uh, the well-known Dulles airport, so to say, structure, where you have a very prominent diaphragm beam through which the cables get anchored and thereby leading to form making. Yeah, you can see them here. You can look at how 2 cables, so it's a kind of a lightweight truss in some sense. The only thing that in a truss, because you have spans such as these, both the bottom boom, top boom, or the rafters would tend to get very heavy. Yeah, in order to bring about rigidity, considering the spans lead to the depth of the members. Here, because they are cables, yeah, you can afford to have the top boom and the bottom boom to be very lightweight, stretched across, and vertical supports, yeah, and vertical supports to help the compression. Yeah, so in some sense you are creating a bowstring truss. This is nothing but a bowstring truss created by uh, heavy compressive members and lightweight tension members. So the truss comprises of the cable-like tension members and vertical compression members, thereby helping in the, yeah, thereby helping in very large spans, yeah, very large spans with no internal support. So you can imagine this. The span is large. It's as good as putting a truss across. The only thing, you're making it as lightweight as possible because you're using a cable and using the dead weight of the cable to help it in some sense by strutting it and creating what is well known as a bowstring truss. I hope I hope these concepts are clear. Yeah, uh, we thought these diagrams were very important, and that's why we're using this as in continuation. Yeah, for the understanding that is there. So how you'd use the idea of the, so as the spans increase, what are the kind of conditions we'd have? What are the kind of conditions we have by because of the sagging of the, because of the sagging of the members, because they are spanned across and because they're spanned far apart, as well as for or based on their dead weight. So how do you use the dead weight of the cable to its advantage? Yeah, how do you use the sagging to its advantage? So you have, yeah, so you get the idea, you get this, you use the span, you use the sagging of the member to use it as a bottom boom of a, like a, that of a truss, and create a kind of a trussing member through perhaps less than 1/3 the material that you'd go about in the case if you'd be using a girder or a truss. Yeah, here are other forms. Yeah, here are other forms, thereby allowing you to use um, suspended girders, suspended bowstring trusses. Yeah, the beauty is the suspended ring. Yeah, the beauty of these members is the suspending ring to get this arena-like forms. Yeah, and how tension members can step back to create, yeah, to create this so to say domed oculus like kind of structure. Yeah, so yeah, if you search on Structural Systems by Heinrich Engel, you'll find a number of these diagrams of the experiments that he's done. A real find for architectural students, structural and form making. Yeah, I'm sure most of you would deal with thesis projects where you'd want to keep your buildings as lightweight as possible, and perhaps these could help. Now we'll come to the last and some of my favorite sets of, or you can say the conventional cable stayed structures. Bear with me for 3 more slides before we can take some queries. Um, here is the first is the well-known model, or you can say all these three are the well-known models for airplane hangars. Yeah, large cantilevered airplane hangars. The first is one using an A-frame and cable stayed, lightweight cantilevered roof. Yeah. The second one, as you see, is a suspended roofing system from again a cable stayed, clearly cable stayed enlarged support system. And the third is what we've already discussed, is where you create bowstring trusses. Yeah, you create cable bowstring trusses to be in a position to get the support that you're looking for. Yeah, so these are, you can't afford to miss them if you're looking at tensile constructions. Yeah, another couple of examples of working with creating creating. So the first to the right is again on similar lines, using the idea of the bowstring truss. Yeah, bowstring girder, you could say bowstring girder using cables. Yeah, here you'd have with a concave roof, the one with a convex roof, an interplay of truss come girder. Yeah, so you'd see a girder at the girder in the center, trussing at the end. Yeah, fine forms with ridges made. Yeah, ridges that come in the center. Yeah, and yeah, we're done with this. Yeah, I'm glad we could show these in continuation to. We could show in continuation to the, so to say, lecture last time. The last time's lecture was more theoretical, based on the kind of the the kind of loading that fell in place, and largely a lot on material, yeah, to make you understand. But I thought that these diagrams would help you um, open up the possibilities to the use of cable stayed and tensile structures. Vikram, would you like to add anything, or we should open it up for questions?
Jimmy, we can open questions. And
Yeah.
after that, quickly take that other video instructions and then we open up for some more questions.
I can wait for, we can take a couple of questions if necessary uh, for 5 minutes before we could go into the next topic. Um, are there any queries? Did you think these were helpful? Did you think these were helpful? This could help you. Uh, Thankfully, these are easily available on the net. Uh, should not be difficult for you to. Again, the same people are missing from the class. Amrit, Chandrajit, all of these people are again missing from the class. I really wonder. Sumek Dhole, Amrit Nagpal. Yeah. Are there any queries? I see some query. What is the material of the slab in the type you showed towards the end? It may not be it could be a lightweight slab. Yes, because uh, once the cables fall in place, they are as good as like a truss. They are as good as a girder. I wouldn't call it a truss. They are as good as a girder. Uh, Depending upon the roofing material, your girder would tend to be lightweight or heavy. So, but naturally, I wouldn't suggest going in for a heavy roof like that, something in concrete. But yes, lightweight metal sheets are some of the best that go in such conditions. Yeah. If you go at the airport and look at these hangars, most of these hangars have lightweight metal sheet roofs. Don't forget large steel companies, be it the Tatas, the Lloyds, yeah, JSW, yeah, Jindal Steel. All of them have a large market by way of these large span structures, airport buildings. Yeah, they are constantly touch with companies who have got bids to build such huge industrial projects. Yeah, so they are all the time working with materials, profiles, forms, yeah, like the domed, like the corrugated domed sheeting, yeah, metal sheeting. Has been a very big hit in industrial buildings. It just gets rid of the. So I have a metal powder coated metal sheet that is powder coated metal domed roof that is so to say undulated. Yeah. and you do not, because of its inherent structural strength, that is the domed roof, that is domed, or not domed, I would say vaulted. Yeah, vaulted sheets. Vaulted sheets, good 20-25 meter spans. Yeah, up to, and big industrial projects all over the Western Corridor. Yeah, the all Western Corridor, right from Gujarat to Agra, yeah, all along the western. If you move around by road, you'd find large number of industries that have adopted this roofing system, yeah, because it just avoids using a structural member to span across. The roof sheet itself, in its profile, has inbuilt quality of spanning. Yeah, so big hit, very big hit. So sheeting roof companies, yeah, metal companies are all the time working with material, yeah, working with roofing materials to be in a position to bring about lightweight, because once you place them at those heights, you don't want to excess them. You want, so the kind of fixing that is there for such roofing systems overlaps to make them as watertight as possible, low maintenance, drainage, all of these. There are numerous criterias, and most important, weight. Yeah, making them as lightweight as possible. The more lightweight you make them, the more cheaper you make them. Yeah, as we all know, steel is measured in weight. So the more lightweight you make them, so the top, so huge sheetings, such huge roof sheetings are usually in metal. They could also be other uh, fibers, yeah, reinforced fibers. So all kinds of FRPs, plastics, all kinds of reinforced plastics, but they don't last. They don't. Their lasting qualities are much lower. Yeah, uh, as compared to roof sheets. Yeah. Was the presentation clear, Shrusti? Otherwise, do you think the typologies helped in understanding how? So one big takeaway was, how can you avoid using a girder or a roof truss by using cable stayed long span structures? Today, could you gather that cable stayed long span structures can be created? I hope that concept has been clear to you in today's class. Yeah, pulling cables across two supports using lightweight struts, pulling another cable across to create a kind of a bowstring girder or a bowstring truss. I hope these concepts have been made clear through these diagrams. Yeah. Anybody else? Uh, Abhishek Gajam, are you there? Abhishek Gajam, are you there? Hmm. Yash Gorecha, are you there?
Yeah, I'm right here.
You thought the presentation today was helpful in some sense?
Yeah, it was.
Thank you. Okay. Uh, I'm just keen to know how many people are around. There's old habits die hard. Yeah. Uh, um, my good friend Mokshit, are you there?
Yeah, I'm here.
How are you doing?
Yeah, it's going good. It was a great presentation.
Oh, don't say all that. I'm missing you, man, with all your funny shoes and
Yeah, same here.
Mr. Vedvrat. Mr. Vedvrat Kelkar, are you there?
Yes,
How are you doing?
fine, fine,
Oh,
fine.
now you've got the grasp of KRVR or yet struggling?
No, I got it.
You've got it.
Yeah,
Good. Keur Mehta.
Yeah,
Keur Mehta, are you there?
yeah, Jimmy.
Okay. Okay. You thought today's class was could help in
Yes,
understanding cable state?
yeah, actually it introduced to me the various kinds of structures, lightweight structures, which I could use it if we end the thesis, right?
Okay. Okay. My favorite student, Kashish Singh, are you there?
Yes, I'm here.
You better pay attention to all the construction classes, huh? Double,
Yeah,
you should see the videos 3 times. You should see all the videos 3 times, huh? Minimum. Yeah. Miraj
yeah,
Sutaria, are you around?
yeah, I'm here.
Okay, good. Oh, Shikhar Tarjane. Shikhar, are you around?
Yes, sir. It is very good to see you
Good, good. Nice.
after so long. Uh,
Yes. Good. I'm glad to hear you. I'm glad to hear you. Okay, I
yes,
see some comment there. Vikram, you'd like to talk to anybody particularly? Some of your The presentation was clear. Okay, fine. We'll share the presentation. I'm sure running through the presentation, all of the 3 presentations we intend to upload such that you should feel free to ask. We intend to upload all the 3 presentations, that is uh, portal, folded plate and tensile and cable state. Um, as a breakaway from so to say taking a lecture, we for the topic of shells we have decided to go in for a very appropriate 30-minute video. Yeah, that the professor is a PhD who's taking the lecture. He runs a well-known portal or a link called civil capsules. Yeah, so if it interests you, you can look at or some of his videos. He's shared a lot of videos on airport constructions. Yeah, as airport typologies, but I found particularly this one on thin shell construction very useful. um, we have also been able to crack how to include audio in our so to say in our presentations. So we're going to try that today by playing an YouTube video that can help you. And the best part is that he's looked at shell construction chronologically. Who are the first who are the first people who attempted shell constructions, and uh, how how the idea of shell developed, who are the people who have been path breaking in this kind of buildings system and technology. He also speaks exclusively and strongly about 2 things. One is the form making part of it, which is very important, which actually lends structural, so to say, less clarity to the built form, as well as the conservation on material. Yeah. So how such huge concrete constructions can be made by using bare minimal concrete, so to say, cross sections. Yeah, and it's largely associated with form making. So without wasting time, I'm glad to see most people are yet around. Abhishek Gazam, if you are there, you please make sure you get in touch with me I'll start otherwise, and kindly keep the uh, so to say questions for the last. Yeah. I think I've gone somewhere else. Can you all hear and look at the presentation? Kindly give me confirmation.
Not yet. We are able to see you at the moment.
Oh, sorry. You can't see the presentation?
Not yet. Jimmy.
Okay, just a minute. Now,
The parabolic arch that forms the front of this chapel spans.
what about now?
Yes. Now we are able to see.
Yeah, able to see the.
Yeah.
Sure.
Jimmy, can you switch off that small box over there?
Welcome back, and welcome to the amazing world of the thin shell, a unique type of structural element that's found in some of the modern world's most exciting buildings. Just to whet your appetite, here's a typical example. Chapel Lomas de Cuernavaca, built by Felix Candela in 1958 in Mexico. The parabolic arch that forms the front of this chapel spans over 100 feet, and it's nearly 70 feet tall. Yet the concrete shell itself is only 1.5 inches